In today's video lecture, we are learning about bonds between metals, and we call those covalent bonds. As you watch this video, feel free to pause or rewind as you need to while you are filling out the notes on the front of your 3.4 handout. Then you will complete the practice problems on the back of 3.4. So far, we've learned about ionic bonds, and that happens between a metal and a nonmetal, and electrons are shared. We've also learned about metallic bonds, and that's how alloys are formed, and so typically that's going to be just metals. Sometimes you'll have a nonmetal in there too, but basically their mobile sea of electrons just mixes. And then today we'll be talking about bonds between just nonmetals, and we call those covalent bonds. The word covalent just means sharing valence electrons. So in this type of bond, it always happens between nonmetals, like I said, and electrons are shared. And the final compound that we have, we call that a molecule. I'm sure you've heard the word molecule before, but this is the correct context to use it. When bonds between nonmetals form, we can either have single, double, or triple bonds form in order for the atoms to become stable by achieving their octet. Just a reminder, an octet, it's when you have 8 valence electrons. However, it doesn't always have to be 8. For example, hydrogen only needs 2 valence electrons to be stable because it's just filling up that 1s sublevel. So as we can see these examples on the right, each hydrogen has 1 valence electron, so if they share it, then they each get to have 2, so they are stable. With oxygen, each element has 6 valence electrons, so they will each share 2, form a double bond to achieve an octet. Nitrogen has 5 valence electrons, so it needs 3 more to be stable, so each nitrogen atom will share 3 of its electrons, bringing them both to a stable 8. Even though the electrons are shared, they're not always shared evenly. If the electrons are not shared evenly, we call that a polar covalent bond. What happens is the electrons are going to be closer to the more electronegative atom. Electronegative just means that it has a strong attraction for electrons. So in this example, we have hydrogen and chlorine bonding together. As you can see, the electrons are much closer to chlorine because chlorine is much more electronegative. So even though the electrons are still shared, there's going to be a much higher electron cloud density near the chlorine. And because there's going to be more electrons over there, this is going to have a somewhat negative charge on the molecule, and the hydrogen will have a somewhat positive charge because it will have less of an electron density. You can kind of think of this as forming poles, like opposite regions, because you have your positive and your negative side. So these compounds, while they are covalent, they will behave a little bit more like ionic compounds, but the electrons are still shared. On the other hand, if the elements have the same electronegativity or just very similar electronegativities, then you'll have a nonpolar covalent bond. So in this case, the electrons are shared evenly. They're not going to be closer to one element or the other, so it's going to be a very neutral atom, and you're not going to have positive or negative regions. So in 3.1, we learned how to draw Lewis dot diagrams for individual atoms just by drawing the number of valence electrons around the chemical symbol. Today we're going to be drawing Lewis dot diagrams for molecules. So you're not just going to be drawing dots for your electrons, you're also going to be drawing lines that indicate bonds. One bond is represented with a line, and it represents 2 electrons. If there's electrons that have not engaged in the bond, then you just draw the 2 electrons together, and we call that a lone pair. You have to make sure that each of your atoms in the molecule achieves its stability by having an octet. Just a reminder though, hydrogen only needs 2 valence electrons to be stable. So let's take a look at a couple practice diagrams. So first we have H2O. So we have 2 hydrogens and 1 oxygen. Let's go ahead and draw our oxygen atom. And if you look, oxygen is in group 6 on the periodic table, so it has 6 valence electrons. Oxygen needs 2 more electrons to get to its octet of 8, and it's going to get those 2 electrons from the 2 hydrogen atoms. So I'm going to draw my hydrogens, and I'm going to arrange them so that the hydrogens and their electrons are going to be facing the bonding electrons of the oxygen. So what happens is that forms a bond, so now that represents 2 electrons, and then we have a bond right here that represents 2 electrons. So just to go through and count them up, we have 2, 4, 6, and 8 electrons on each oxygen. And remember, each of these bonds represents 2, so that's going to be 2 electrons per hydrogen. So that is going to achieve stability. And that is what water will look like as a Lewis structure. Moving over to hydrogen cyanide. So we have a hydrogen, which has 1 valence electron, carbon, which has 4 valence electrons, and nitrogen, which has 5 valence electrons. Right now, you might not really recognize or understand why I'm drawing the dots in the way that I am, but the more Lewis structures you draw, the easier it'll be to kind of position those electrons in the correct areas so that you can draw the bonds nicely. So we know hydrogen just needs 1 more electron, so we're going to assume that'll form a bond there. If we count up our electrons on carbon, we've got 1, 2, 3, 4, 5. So carbon needs 3 more electrons to become stable. And so this one, pretty obvious. We still need 2 more. What happens is we also have bonds forming up here and down here, and that's going to be a triple bond. If you were to actually look this up online, it would be drawn a lot neater, so I'm also going to draw that for you. So it's really going to look more like this as a Lewis structure. So you can see we have a single bond between the hydrogen and carbon, and a triple bond between the carbon and nitrogen, and the nitrogen also has a lone pair on the right side because those electrons were not involved in the bond. Down here, NH3, we've got some ammonia. So again, nitrogen, 5 valence electrons, so it needs 3 more. You can probably predict that it's going to get those from the hydrogen atoms. So I'm going to draw those in and go ahead and connect the dots. So now nitrogen, if we count it up, we've got 2, 4, 6, 8. Great. Nitrogen is now stable, and each hydrogen has 2. Over here we've got some carbon dioxide, so I'm going to draw my carbon. It has 4 valence electrons. I'm going to draw an oxygen on either side. And remember, oxygen has 6 valence electrons. So carbon needs 4 more, and each of these oxygens needs 2 more. I'm going to move this oxygen over, it's a little too far away. I'm going to go ahead and draw those bonds. So these ones you can probably recognize pretty quickly. So now oxygen still needs 1 more, and carbon is all set after drawing those. And I am going to clean that up to make it look a little bit neater, so it's drawn in the correct way. But basically you'll just have a double bond between each oxygen and the carbon. So if you double check, count those lines up, we've got 2, 4, 6, 8. And then if we count up for each oxygen, 2, 4, 6, 8. So they are stable. Next thing we're going to talk about is how to name covalent compounds. So we do it the same way as the ionic compound, where you keep the first element, it keeps its name, and the second element gets an "ide" ending. However, we also have to include prefixes because covalent compounds don't always bond in the same ratio. So like, for example, you could have carbon and oxygen as CO2, but you can also have carbon and oxygen as just CO. And so you have to use prefixes to indicate that. Your prefixes are right down here. And so we use that to indicate the number of atoms in the molecule. Typically, the mono prefix we don't use unless, the only time I've really heard it is if the oxygen is the second element in the compound, you might hear mono. So for example, like this here would be carbon monoxide. And just to show you, oops, so that would be carbon monoxide. You might be thinking it should be carbon monoxide, but if you have like 2 of those vowel sounds in a row, then you can just drop one of them and you can have monoxide. So for example, if you were doing like tetra with oxide, you would just say tetroxide or pentoxide. So you get to drop one of those vowels. So right here we have NH3, known more commonly as ammonia, but when we use our prefixes to name it, that's going to be nitrogen. And then we have 3 hydrogens, so tri, and the second element gets that "ide" ending, so trihydride. Next we have H2O, so that would be dihydrogen, monoxide. So if you want to sound really smart when you're saying water, you can call it dihydrogen monoxide. Over here we have carbon dioxide, which should sound very familiar. And then finally we have silicon tetrafluoride. So that's it for the naming. That part's pretty easy. I might also give you the name and you would have like this, and you would have to write down the chemical formula, or like CO2. So when you flip to the back of your 3.4 paper, the top section is going to be drawing Lewis structures, just like what we did up here, and then the bottom you're going to be practicing naming or interpreting the names. There is one typo I want you to take a look at. So number 8 up on the top, it just says PO3. That's actually a polyatomic ion. It's phosphite, and I forgot to put that it has a -3 charge on it. So just go ahead and add that to your worksheet on the back. Make sure you indicate that there's a -3 charge on that phosphite ion. And so just a reminder, if something has a -3 charge, that means it has 3 extra electrons. So when you draw out that Lewis structure, you're going to tack on 3 extra electrons to the atoms that need their octet fulfilled. So I would like you to pause this video, try to get through those practice problems up on the top. I am going to do number 1 and number 2 so that you can check your work. But pause the video for now, try to do 1 and 2, and then go ahead and press play and check to see if you got the right answer. Okay, so hopefully you just did 1 and 2. I'm going to draw those out for you so you can check your answers. So we have carbon. It's in group 4, so it has 4 valence electrons, and we also have chlorine. Chlorine has 7 valence electrons, and I'm going to draw that lone electron on the side that's like facing the carbon atom, because I am assuming that's where the bond is going to form. Just a little shortcut, especially when you're drawing like the halogens. They have a ton of electrons because they have 7, so if you have to draw a bunch of them like that, you can actually, there's a shortcut. Instead of drawing the dots as a lone pair, I'm going to change my color so you can see it better. You can also just draw a line, and each line, it just looks like one of those bond lines, represents a lone pair. So I'm going to go ahead and connect those. And so when you count these up, each chlorine has 8, and each carbon, and the carbon atom has 8 as well. To show you number 2, you've got 2 carbons, each has 4 valence electrons, and you also have 6 hydrogens. So let's go ahead and draw a bond between these carbons, because that's kind of obvious that a bond will form there. If you count these up, you will see that carbon currently has 1, 2, 3, 4, 5 valence electrons. So it still needs 3 more. So each carbon needs 3 more valence electrons, and it's going to get it from those 6 hydrogens. So I'm going to draw my hydrogens around the carbon atoms, and I'm going to draw them in a way so that they will line up perfectly, so I can draw those bonds. So I'm going to go through and connect those dots. Oops. So you can see that now each hydrogen has 2 valence electrons, which that's what it needs to be stable. And when you count up the carbons, there's 4 lines, so 2, 4, 6, 8 valence electrons. So now carbon is stable. So go ahead and finish the rest of your 3.4 on the back, and I hope this was helpful.